All right. Hi, welcome. My name is Nick, and welcome to a video on belt and just general design and use of belts in FRC. What I'm going to be doing is giving a little bit of background on why you'd use belts, where you'd use belts, and how you use belts or FRC in this video. Um, I have become, in this case, I'm talking specifically about timing belts. So toothed belts that have a pulley. Those are typically in industry called timing belts. Um, and they are very, very useful. They're a really great way to get high quality, low cost power transfer in a variety of situations, assuming that you can afford the time that it takes to order and receive belts. Um, and belts are really like they're just such a flexible and easy thing to use, assuming that you have CNC capabilities. If you don't have CNC capabilities, this video probably isn't for you. Um, if you have a DRO manual mill, or you're just good with a regular mill, you could probably do some stuff with belts, but where belts really shine is when you have access to some sort of CNC, um, because that just makes it really easy to use them. Um, so where would you use belts in an FRC robot? Really all over the place. If you look at the Andy Mark Kit of Parts drivetrain, um, that uses belts for the drivetrain. If you look at um, all sorts of robots, you'll see belts driving shooter wheels. You'll see belts driving conveyor systems. You'll see belts as the conveyor system. You'll see belts driving climbers. You'll see belts driving elevators. Belts are really all over the place in modern FRC. Um, and that's partially just because CNC has picked up so much, and it's um, partially because we've learned new and better places to get belts from industry. So let's talk a little bit about what I mean when I'm talking about belts. So for a belt, you're going to see a few different things in modern FRC. So if we go to VexPro, um, and we go into their motion pulleys, right, you'll see they have a couple different options. They got timing belts, 9 millimeter width, HTD timing belts, 15 millimeters and 9 millimeters. So I people in FRC make a really big deal about GT2 versus HTD. Um, in this case, we don't actually care very much about that distinction. In the vast majority of cases, I would argue in FRC, you don't care about that distinction. What you care about is this number right here. You care about that it's a 3 millimeter pitch for the GT2. Care that it's a 5 millimeter pitch for the HTD. Um, what that lets you do, that's basically the number that determines the size of health. So like on a number 25 chain, you have a 1/4 inch pitch. So every link of this, every link of that chain is a 1/4 inch apart, right? There's a 1/4 inch spacing. Similarly on a belt, right? A full, not link, but basically cog of this is 5 millimeters. Um, and you can look up all the math that you'd need to like transfer that back from, say, whatever, calculate that from two pulleys and the distance and whatever. Um, the reality is like, and I would highly encourage you actually to do that if you've never looked at that. But in the vast majority of cases, what you're actually going to want to do is use a calculator for that. Um, So those are the two main distinctions. So profile and pitch. We generally don't care very much about profile. 971 might care about profile. 254 might care about profile. Um, Assuming that this is being watched by a normal team you don't really care about the profile. The pulleys are, you can print the pulleys basically the same, right? The method that I'm going to show you for creating the pulleys for these works for 3mm GT2, um, works for 5mm HTD, works for 5mm GTD2, works for 5mm for 3mm HTD. Like these all, it works on those. The tooth profile is largely compatible. You do miss out technically on some stuff, but it doesn't really matter. Um, so I'm going to show you some of the calculators that we use for here. So first, I'm going to pull up Spectrum's calculator. Spectrum is, again, I did a video on this and how I use this for my Inspire NC robot, but their calculator is just fantastic. Like props to Spectrum for putting out fantastic resources. Props to Alan Gregory for that. Um, but what you're looking at is actually these two calculators. So say I want an 18 teeth pulleys, and I whatever want to throw a 60 tooth pulley between those two, right? That'll give me a dead center to center distance of 4.134. So where this would basically come in here is if I were to go and start sketching things and I wanted to have some pulley thing here, this would be 4.134. I'd throw some bearing holes on either side of this. These are probably, because this is FRC 1.25. And then like maybe I want to do something else with this, right? So another one over here. And another one over here, right? So what I'm doing is I'm setting these all equal. These are all just going to be the same size thing. And the reason I'm taking the time to do this is because I'm going to be kind of gradually modeling something out of this too. So I have no idea what this belt mechanism would be for. Probably not anything super useful. But we'll just pretend this is a real thing. So what I'm going to do here is then I'm going to just take a little bit of time. Put some stuff between those. And then I'm going to be super lazy. Use this. And let's see if we... Oh, that might have been a little bit too much. Let's... That might be fun. I have no idea what that fillet radius is. So we got a plate here. It's made from a sketch. And what we're going to do is we're going to want to run belts from here to here to here. I'm not going to worry about how we're powering this. We'll pretend that isn't a real issue. So like I said, we have these dead center to centers here. So this is the conventional way of designing belts. So a lot of times people will just say, throw a dead center on there, dead center to center, and that's fine. That's not always 100% truth, right? And there are cases where you want to go over the dead center to center, and cases where you want to go under the dead center to center. So let's talk a little bit about when you would want to go over. So I might want to increase this by a very small amount if I wanted to put more tension on the belt that would help us reduce some backlash, reduce some skipping that's belt induced. Now on an X drive shaft, that backlash minimization isn't going to help you because typically hexes are awful for backlash. At least the stuff from first suppliers are. But for the skipping, it might help you. Yeah, I don't typically do this very much because I don't tend to use belts in those situations, but sometimes there. The main drawback on this is that it's going to increase the force on your shafts. So if I decrease this to say, um, and this is how I always do these adders. I would always keep the dead center there because if you don't keep the dead center there, you might forget that you changed it later. So let's say it's minus 0.04, right? Or sorry, plus 0.04, right? That's right. Okay, cool. Plus 0.04. So what that would do is that would also increase the tension between these two shafts, right? So if these shafts were cantilevered, which you would often do, um, with a belt run, you might run into issues there because they're going to pull towards each other, and it might result in things bending. So generally, I try to avoid this unless they're very well supported in aluminum. Like that's the kind of thing that you use on an arm or some sort of really robust thing that might benefit from that kind of control optimization. And usually in that case, you're really probably just fine doing a dead center to center. Um, where you reduce things is a little bit more interesting. So you can actually reduce belt runs by a significant amount and see some good benefits. So, like if this was part of an intake mechanism, maybe, I would say that you're probably good anywhere like between 0.02 and 0.06 as a reduction. Um, and I've run actually as low as minus 0.06, minus a 16th basically of an inch on there. What that does is um, it'll reduce tension on the belt, which has some great benefits as far as reducing current draw on the mechanism. It might increase skipping, but on stuff like intakes, that's often not a big deal. So I'll pretty frequently find myself reducing somewhere in that 0.03, like a 30 seconds to a 16th of an inch, right? Um, and that's fine. Like that's totally fine. Also, places in between there are there. So if you looked at this and you said, I spec this and point in 4.1 is actually what I would prefer this to be. That's fine. Like take that down to there. Like a good that's an acceptable reduction, and you can do a little bit of playing with stuff to get dimensions that you like there. Um, you have to be a little bit careful with that because you can run into weird situations where you have more tension on some part of it and less tension on others. So I would always recommend trying to stick with a like consistent minus a 32nd, minus a 16th, minus whatever midway between there is, right? Um, but like it can work, right? You can make it work in those ranges. Um, so big things there. Um, so let's say yeah, so take that right. And you can see how I defined this. That's how I would always recommend defining something around this, right? Is you want this to be flexible to that. Uh, let's see. So now, like, let's answer that question of okay, how do I model these belts? There are a couple of main tools that you'd use to do that, depending on which one you like. So personally, um, I find myself largely using Julia's contextless belt. So what this does is it lets us do an in-place belt from these 2 points with an offset. And then I'll probably have to change these 18 to 18, right? Um, and that's a pretty good thing. So these might be more like 0.05 offset or something like that, or half an inch offset from there. Thickness, you don't typically need to mess with that. And then this is a 9 millimeter belt. So you can also make this like be a 15 millimeter belt. It could be a 15 millimeter belt. What's that distance here? Yeah, so close to a quarter, 1.25 inches, which is basically right there. So we have a belt. That's one way to get a belt. That's my preferred. That tends to be my preferred way of getting a belt. If we hide that, there's another great one that I saw on Chief Delphi recently. It is this belt generator. And I'll link all these in the comments, right? So this does things in context too. And you'll see this is complaining. It doesn't like that center to center. It has, it's just not a fan there. Even if I let it select something, it's not a fan there. So what was that size? So it's, we wanted custom length belt, so 60 teeth, 18 millimeters, yeah. And it looks like we got something messed up there. Not 100%. Ah, there we go. But yeah, it's still complaining about this. These are going to be 18 to 18. And one of the things I really like about this one, that I wish was also done in Julia's, though I'm of mixed minds about it, is this will actually let you just throw in the custom pulleys that you'd want in there. So you can see that this is not, these custom pulleys aren't perfect. So what I find myself usually doing is deriving a custom pulley into stuff like this. I'll show you how to do that later. So this one's fine. I tend to not use it though, because even though it checks a bunch of the boxes on my workflow that I typically do for this. But I don't like having a red thing telling me that all of my belt dimensions are wrong when I intentionally made them that way, right? Like it's annoying. Also, it defaults to this composite part, which questionable. So we'll cancel that, and we'll just go back to Julia's belt, which is great. Now I'll show you how I would derive these. So, oh, and then the other thing here. So even I find myself even in cases where I have duplicates. This is one of my big rules. If anybody had listened to me, is I hate duplicate parts. Like, you have to be really careful about when you have duplicate parts. In a case like this, I'm often fine with it. The reason being that I find myself oftentimes changing belt dimensions later. So it just saves me effort to say, these are all going to be separate belts and then add them up later, over doing that over like making these one and then doing all the constraints here. This also saves time when we do if we did this, inserted these into a part studio. So I'll show you what I mean by that. So then this is going to be 0.5. Oh yeah, and then here, this is where you would change, like if I wanted this to be a 3mm pitch, right, I could change it here. That would be fine. But yeah, 5mm pitch there, 15mm belts, right? Cool. So now we've got some 15mm belts here. And we're gonna want some custom pulleys. So in some cases you can just insert the MKCAD custom pulley into your thing. In this case, I'm going to show you a few different things you can do with custom pulleys that are useful. So let's talk about, where's my derive? Here's my derive. So other documents, let's bounce over to MKCAD, pop down to pulleys, and configurable 5mm HT timing pulley. So an 18-tooth pulley for 15 millimeters. So if you calculate what 15 millimeters is in inches, 15 by 25.4, right? You end up with 0.59. So what I'll typically do is make the width on these 0.625. These will assume we're on a hex and that we want it to be like a close to a 5 point to a half an inch one. And then what these will do is the flange widths here, you'll see when I end this, you have two flanges on this. So this is basically adding 1/8 of an inch to this. So that pops up this width to 0.75 inches, which is convenient. Similarly, if we were to do a 9 millimeter, I would make this width 3/8 of an inch. And then we'd end up with a 1/2 inch wide pulley, which is very useful. So these are all good. I'm going to turn off the main connectors because the main connectors are inconvenient. And we'll insert that. So if this is your first exposure to Derive, basically the way Derive works is it takes a part from some other place and lets us put that into a part studio. So let's say I want this pulley here, and then I want to make a double pulley here because I am lazy and I don't want to print two of the same pulley. That would be silly. So what I can do is start doing some transforms. And in this case, I love transform by mate connector. Transform by mate connector is one of the best parts of Onshape's drive workflow. What that lets us do is just take those two things, and it's exactly like constraining something in an assembly. And that's just some good stuff, right? And we don't want an offset on here, so we actually do want an offset on here, but that will be a second one. I'm gonna do another one over here. It's gonna look like this. So transform by mate connectors, and then that one to that one. For one mate connector here, two mate connector here. Flip that and make that a copy. So I end up with two of them because this one's going to be changed. Then we'll do another transform. That's going to be a transform by XYZ. So these will be, I think this is it this one? I am, so it's probably gonna be too much, isn't it? So 3125, it seems reasonable. Or 55 plus 30-second. It's probably gonna be like 360 points, maybe. Something like that. Yeah, that looks good. We've got that there. So now we got this one. This one is in its right position. And so in this case, we're like, let's say I want it to be like this. But there's a bearing here. So there's going to be a bearing. There's might be a bearing flange. Actually, you know what? This is just going to be easier to throw in an assembly. So I'm just going to chuck all this in an assembly. And what am I doing? Group. Just going to fix one of these. So we've got this in assembly. And I'm going to start throwing in a few things. So let's say I want a bearing in here. So let's there's the hex. That sounds reasonable. So we got a whole bunch of those. And so I don't want to print a separate spacer here. I don't want a spacer that's whatever the heck this distance is. 0.234. I don't want to torture a freshman by making them lathe that or whatever. I could 3D print that as a separate spacer, but why do that when I'm already going to print this pulley? That's just silly. So what I can do then, because this is a derived part, I can do this. I can just add that straight onto there. And then, because when you do a pulley, you do something like this, you only want to contact the inner race, this inner bit, because otherwise it'll have friction on a static part. So I think that's 0.75. So I want to take this down to 0.75. So or less. So I can throw this on there. 0.2, it's reasonable. Give me more. Oh, wait, it's not going to like that because like that, right? And this will work any way that you want this, right? So if you wanted this to be something really specific and all that, like you could do that. I'm just doing it simply for thing here. So now I have a nice custom pulley here. It only contacts the inner race and has perfectly spaced this. And we'll probably want to do the same thing. So let's do that over here. And this is a cool thing that Onshape will do. It knows that those are two separate parts. It'll let you just merge those both into there. And then it automatically did that because Onshape is awesome like that. So now we've got two of these parts, and this part is identical. But that's probably not exactly what I want to go on there. So let's back this up. And we're going to want to do another transform here. And just, there's that one inch is good. So like that, right? And then what we can do is we can use these. And word scope, both of these. Now we have one pulley here. I can do this and we get everything back. Now we have a couple of custom pulleys. That should work pretty nicely for our contrived example. And if I was confident that these are going to be the exact ones that we use elsewhere, what I can do is I can start taking these and throwing them up here, right? This is, say that's the right place. That's the right place there, right? So now we have a bunch of custom pulleys. It's awesome. So I hope, oh, I was going to give you a few different pieces of advice on 3D printing and stuff like that. So one, don't be afraid of 3D printing pulleys. Like almost every pulley in FRC can be 3D printed. High load stuff, maybe not. But like vast majority of stuff that you want to print in FRC, you can print in FRC with a pulley. Sometimes you have to be careful to expand things or something, whatever, or reinforce it or give it something. But generally you can print it in FRC. That's part of what makes these things simpler. I also have a few different preferred vendors for this, so I love getting stuff from Vbeltguys, and anybody from the FRC Discord is laughing right now because they all call me a Vbeltguys shill, and you know what? It's true because when I can get uh, so let's take a look at this. So here is a 60 tooth belt in Vbeltguys at Vbeltguys land. $1.84. If we still had a bomb, that would be free on the bomb. You wouldn't have to count that. Let's pop over to Vex Pro. How much is a 9mm belt, 60 tooth belt here? $8. I love Vex Pro. Vex Pro makes fantastic products. But I find that my team is, like many teams, sometimes broke. And sometimes getting 4 belts for the price of one is a really good deal. So I tend to go to Vbeltguys and print my pulleys. is pretty much what I'm saying here. Another great supplier is Polybelt. So shop polybelt.com. They have a little bit more selection in some ways, a little bit less in others. One of the things I really like about these guys is that they have steel and Kevlar timing belts, which can be really useful if you want to power an elevator on it, because elevators sometimes get a lot of force, and that can make it hard to um, use a normal belt on there. Sometimes they'll break. So, anyways, those guys are great. The other reason to do these in place is because it can save you some replication time. So for these ones, I'll just do a linear pattern here. So let's say I had more pulleys. Right? Like you can just pattern these, and you can do that a bunch, and then you don't have to manually constrain all these belts, which is a pain, especially when belt stuff dies. Belt constraints die if they're the wrong size. So anyways, that's my show on belts. If you have more questions about belts, always feel free to let me know. Comments, give me a button, Discord, Slack, Chief Delphi, wherever. And I will see you next time.